Hello everyone, and thank you for joining me today for the Introduction to Materials for Engineers virtual lecture course, which is a prerequisite for engineers looking to take my Nuclear Materials lecture course here at Cambridge. This short introductory course is designed to teach engineering graduates the fundamentals of material science and metallurgy in order to better understand my lecture course focusing on materials in the nuclear industry. Many of you will have had little to no prior education with respect to material science, and so this course will cover a number of the fundamentals from crystallography and microstructure evolution to mechanical behavior. Now, material science is just one of the many disciplines within the nuclear industry, but it is a most important one. The decisions we make with regards to the materials we use in, for example, reactor design, have great performance, reliability, and safety implications. And at the heart of this is materials degradation. And materials degradation is the life-limiting factor of a nuclear power plant. In almost every case, the primary obstacles in bringing the next generation of nuclear power plants to fruition are materials challenges, be it due to the high temperatures involved, the corrosive environments present, or, as we'll see, the effects of radiation. There is a lot of opportunity to really make your mark in the nuclear industry as a materials scientist, which is one of the reasons why I started to specialise in material science. Now, evidently, if these material challenges are so numerous, it's almost impossible for me to cover all of those in one lecture course. And so we're going to focus specifically on the most prevalent issues: the effects of radiation on structural materials and in the reactor core. Because as we'll see, radiation can change the shape of materials, which will cause volume increases of some tens of percent. It can increase the hardness of materials fivefold, reduce their ductility and toughness, and accelerate general corrosion and other aspects, or even introduce entirely new corrosion phenomena only ever seen when in the presence of radiation. Now, I've constructed a set of lecture notes to accompany this introductory course, which are separate to the main course notes, but these set of notes are comprehensive and contain more than you need to succeed on the main nuclear materials course. However, material science is obviously a very extensive area of science and engineering, far too large to cover in one short introductory course. So should you like to understand things in a little bit more depth, I've suggested at the bottom of the front page a number of useful books that will carry you through comfortably into a career in material science. If I had to choose one companion text for this course specifically, I would probably recommend Mike Ashby's Materials Selection in Mechanical Design, which I've made sure is available within the engineering department library, and likely your college libraries have them too. Should you not be a bookworm and feel a book is a little bit too much, you're probably in the wrong place. But we also have online resources which have proven excellent for understanding the very basics of material science. So please look up doitpoms.ac.uk. So I've given you the link in your notes, okay, on page 2. So please look up doitpoms.ac.uk and look at the packages that I've listed here on page 2, because they will help. So let's begin. And we'll begin with intrinsic and extrinsic properties of materials. Many of you will have heard of materials' strength, toughness, and stiffness, but you might not know what the difference between them is and what influences these properties. So we'll start there, I suppose. Any material, if it's going to be used in an engineering application, needs to hold itself together. Yeah. As such, mechanical properties are very, very important. And how well materials hold themselves together is related to how they respond with respect to stress and strain. So what is stress and what is strain? Well, the image here shows a cuboid under a load on page 3. Cuboid under a load caused by forces applied on a pair of opposing faces, acting normal to one another and perpendicular to the faces. Yeah? And that generates a normal stress. And that is denoted by sigma. So sigma denotes stress. So stress is equal to the force over the area across which it is applied. Yeah? So sigma equals F over A. But what about strain? Well, the normal strain is the relative change in length along the direction of the applied forces. And that is denoted by epsilon, i.e. epsilon equals the change in length over the original length. So these strains can cause deformation. And that deformation can be either permanent, inelastic, elastic, permanent, inelastic, or temporary, elastic. And if we move on to the next page, we'll see for elastic deformation. Well, in elastic behavior, what it means elastic is the strain in the material will decay to naught when the applied stress is removed. As such, we call that process entirely reversible. There's no permanent deformation. With stress and strain linearly proportional and a function of the Young's modulus E. Now, you might think Young's modulus, what is that? Well, the Young's modulus is an intrinsic material property. It's a characteristic of the material and not the component the material is made out of, or made into, rather. So it's dimensionally independent. And there is a wide range of different materials with a wide range of Young's moduli, as shown in the figure here, with ceramics having a relatively high Young's modulus in comparison to the lower Young's moduli possible for polymers. And on page 5, you can see, well, what determines a material's Young's modulus? Well, it's a bit beyond the scope of the course, but it's related to the shape of the curve shown here for the interatomic bond energy versus the interatomic spacing. Because Hooke's law, I'll give it to you briefly, Hooke's law only applies over a limited range of deformation. It corresponds to a linear approximation to F, to the force Fx, passing through the point x0, 0, where x0 is the unstressed length. Okay? And integrating Hooke's law gives a potential energy that is parabolic about the minima at x0. Now, that might seem a bit confusing, and there's a more detailed explanation available through the Do It Poms pages, should you wish to delve further, as we've got a lot to get through in this lecture series. So I'm not going to focus too much on that. It's not of vital importance at this stage. So that's elastic deformation. Okay, so it's reversible. What about plastic? Well, the yield stress represents the onset of plastic deformation. And this yield stress is shown in the stress-strain curve below. The initial linear region that you see at low strains, that's the elastic region. And that's where Hooke's law is obeyed. The preceding region, after the yield stress is reached, that's where plastic deformation takes place. And the difference between these two curves shown is the work hardening rate, which we'll talk about in a moment. Now, yield stress is permanent deformation, and is an extrinsic property, not an intrinsic, but an extrinsic property, often showing a wide range of values for any given type of material. You can have one particular composition of steel, you can have a wide range of yield stresses depending on what thermomechanical processes you put it through. So you can easily manipulate the yield stress through heat treatment and mechanical working, as the yield stress in metals is related to the crystal defects known as dislocations. Okay, because metals, most of the ones we're going to be looking at, these crystals, metal crystals, crystalline materials, and they have defects in them known as dislocations. And it's those dislocations that govern plastic flow. and we'll focus on them in more detail later, don't worry. For now, you just need to understand that defects in the crystal structure are called dislocations. They are a type of defect, and they're created and move as you deform the metal. So as I bend a copper bar, I'm creating dislocations and I'm moving them as I bend that bar. I.e., the energy I'm putting into the bar when I permanently deform it is going into the creation and movement of dislocations. So heat treatment and work hardening can change the yield strength of a material. Well, how? In fact, some of you are probably thinking, what on earth does work hardening mean anyway? Well, you can consider work hardening as the increase in yield strength of a material as it plastically deforms. So as you plastically deform this bar, it's getting harder and harder to bend, which is what happens with copper bar. As copper bar work hardens. And this is because as you deform the metal, the dislocation density tends to increase and the dislocation mobility is hindered, thus making it harder to deform the material. So on a stress-strain curve, if a material work hardens, then you'll see a high gradient after yielding, as you see in graph A there above. And such stress curves are of course dependent on temperature, as with increased temperature, dislocations are more mobile and allow their removal, which in turn softens the material. So we'll move away from this. Let's take aluminium. For example, aluminium shows a low work hardening rate when deformed at high temperature, despite having a high work hardening rate at lower temperatures. So to summarize, that the strength of a material is the resistance to plastic deformation and depends on both the microstructure of the material and the temperature you're testing it at. Now there's some other terminology we need to get our head around. Some of you will have heard of material hardness. Now that's also a measure of the resistance to plastic deformation, but it's derived from a specific test method, far more convenient a test method than, say, a tensile test used to produce these stress-strain curves. And it uses a localized compression at material surface. You have a little diamond, you compress it. So they're not the same, but typically if a material has a high yield strength, it has a high hardness. If you increase the yield strength, it increases the hardness, because you're really sort of measuring the same thing. Now if you move on to move on to page 7 here, we'll move on to toughness. Toughness is another word we need to understand. Toughness is the measure of resistance to cracking. Okay, so it's separate to strength. It's the measure of resistance to cracking, not deformation. Cracking. If you take an existing crack, shown on the figure below here, apply a load to a cracked sample and it causes a stress to concentrate at the tip of that crack present. And that concentrated stress can cause that crack to grow or propagate. On the other hand, if you have plastic flow at the crack tip, shown on the right-hand side graph, i.e. the movement of dislocations causing plastic deformation, the crack can be blunted and crack growth is much less likely. Yeah? So if you've got plastic flow, cracking is less likely. So typically materials that are permanently deform easily, so very plastic materials, are less likely to crack. And those that do not deform easily, known as brittle materials, they're more likely to crack. So we can think about it in terms of strength. So increasing the strength of a material in most cases will reduce the toughness of said material. Yeah, because when you strengthen something, it can take less energy by plastic deformation. And because there's limited plasticity, it's going to be a brittle material. Now there are ways that you can increase both characteristics, notably reducing the grain size of materials, but I'll talk about that later. I don't want to overwhelm you. So to make sure our terminology is clear, a brittle material has low toughness and cracks with little to no deformation. A ductile material has a high toughness as a lot of energy must be input to cause it to crack, as it must plastically deform significantly before it fails. When I say ductility, ductility is a measure of how much strain a material shows before it fails. So it's related to that plasticity. I know that's a lot of terms to get your head around for those that haven't done material science before, but you'll get the hang of it. I did. I wasn't a material scientist. Now, I strongly suggest you go back over this in your own time, like I do for all my lectures, but here it's especially important if you haven't done material science before, because now we're going to move on to microstructures. Because most materials we'll look at in the nuclear materials course are polycrystalline, and that means that they're made up of multiple crystals. And crystals are an ordered lattice of atoms in a tessellating, repeating pattern. And these crystals are called grains. And between each grain are grain boundaries. And if you look at the graph here, this is what you see. At the bottom of page 7, you see these grains. They're a bit like bubbles, soapy bubbles. Yeah? Each one is a grain. And the boundaries are the grain boundaries. And they are defects. If you take a polycrystalline material and heat it up to a reasonable temperature where the defects can be removed, that's known as annealing. So when I say annealing, that's what I mean, heating it up, removing that damage. And when you anneal such a metal, these grain boundaries will begin to move or migrate. And they do that to reduce the overall grain boundary area, behaving as though they have a tension. Yeah? So the material is effectively reducing its defect density by growing the grains, and in doing so, reducing the grain boundary area per unit volume. Now, if you were to look at a grain boundary junction, i.e. where 2, 3, or 4 grain boundaries meet, intersect the junction, the tensions mechanically balance and cause interboundary angles to consistently be around 120 degrees. And because of that, you get the pattern that we see in this micrograph, in this figure in 2D, similar to that foam I mentioned, like a soapy foam. And that's why a lot of materials end up looking like that. Isn't nature magical? So to prove a metallic grain is a crystal, you could deform it, which is what you see here for a single crystal of cadmium, where the bands are slit planes where dislocations operate. The photo below that shows a polished surface that's been etched with a chemical to reveal the individual grains. It eats away preferentially at certain microstructural features and shows their boundaries. The parallel-sided bands crossing the grains, they're called twins, but I'll explain those later. We don't need to understand that now. But let's jump to page 9. So we've mentioned work hardening. Well, if that working is done at low temperature, it's called cold working. And cold working is useful. It's a very useful mechanical process to change a material's mechanical properties. Okay. Now, cold work can mean any mechanical processing at room temperature, such as rolling, forging, or extruding. And it causes grains to change in shape, increases the defect density, i.e. the number of dislocations increases, as does the number of vacancies. Vacancies are holes where atoms should be. And this affects, the number of vacancies affects how easy it is for atoms to move, to diffuse, because it's easier to jump with holes. So here I've given you a schematic of an annealed polycrystalline square of material, that little square with the grains. And below it, I've shown what it would look like after it's been cold rolled, for example, at room temperature. Okay, so you can see the grains have elongated in the rolling direction, and you've got some defects, you've got this damage. So you've produced dislocations. Now I know we've stormed through a lot of new terminology today, but this is why I've given you this set of notes. So after lectures you can go over and review the content, make sure you define each term correctly. As unfortunately there's a few more to come. Possibly one of the most important now, phase, the word phase. So what's a phase? A phase is a region of a material with a certain crystal structure and or composition that is different to another in the material. So a phase is a region of a material with a certain crystal structure and or composition that is different to another in that same material. A physically distinct form of a material is also known as a phase, when the material can exist in different phases under different conditions of temperature or pressure. Say water, like the phases of water. You've got steam and ice, water, steam and ice. They are three phases of H2O. They are also in three different states though, and phases need not be of different states. For example, there are several phases of ice itself which differ in how the water molecules stack and pack together in a certain order. And these different phases will form depending on what the temperature or pressure is where the ice is forming. Bet you didn't know that. More exciting things about ice. Probably a bit more relatable though is probably the different phases of solid carbon. To name two, graphite and diamond. Very different properties, but they are two different phases of solid carbon. You know, you don't want to give your partner a graphite ring. It won't last very long, the relationship or the ring, frankly. I would suspect. You probably want to stick with a diamond. Now, I've mentioned the term microstructure a few times today, so let's define what a microstructure is. Well, the textures observed under a microscope, like the schematics I've shown you, are called the microstructure of the material. And altering the microstructure of a material plays a key role in altering the mechanical properties of said material. So let's give it a go. What kind of microstructures are there? And how do we make them? Well, steel is always an appropriate candidate when trying to explain a topic in material science. At least for me. And although you might not think it, steel is quite complicated. And all steels are certainly not the same. So here we're going to take a generic high carbon steel. Basically iron with quite a fair pinch of carbon. Around 1.4 weight% to be precise, for this example. This is the sort of steel that you'd use for high strength knives and other cutting tools that need to be quite wear resistant, i.e. hard. Well, if you look at the micrograph below, this is a microstructure of one such steel. Looks complicated? Yeah, that's because it is. Let's go through it. The clear white bands that you see are a carbide phase called cementite, which is Fe3C, iron-free carbon, as in Fe3C. And this carbide here has formed along the grain boundaries. I'll explain why later. But it forms as you cool the material slowly, around the cubic close-packed austenitic iron. Don't worry if cubic close-packed doesn't mean anything to you at the moment. I'll explain that next lecture. It's how the atoms pack themselves together to form a crystal. There's different crystal structures. Don't worry. Now the zebra-like interior of the grains that you can see in the micrograph, that's called a eutectoid. It's a eutectoid intergrowth of two different phases, forming these very fine lamellae of cementite, the iron carbide, and alpha iron, aka ferrite. So that's more pure iron. Another phase, that's just another phase of pure iron, and it's body-centered cubic. I've mentioned austenite, that's face-centered cubic. That is another phase of iron. And that eutectoid structure of cementite and ferrite has its own name, obviously, because everything has to have its own terminology. It's known as pearlite. Yeah, that zebra pattern is known as pearlite on account of its mother-of-pearl-like iridescence caused by optical diffraction effects. And all these different phases can be produced in different volumes depending on the applied thermomechanical processing. So it's bloody complicated. So how can we model or predict what microstructure is produced for a specific composition and a specific thermomechanical process? Well, fortunately, we've got phase diagrams. That's where they come in useful, which you can see on page 11. This is a phase diagram for the iron-carbon system, and we can use this diagram, which shows the phases stable at equilibrium. i.e. stable after infinite time for a given temperature, because you've got temperature on the y-axis and carbon content on the x. You can see that the carbon, obviously iron is the balance, you can see the carbon range and temperature range at which the cubic close-packed austenite phases stable. Yeah, so you see the top left of the graph here, you see austenite. So this, across this temperature range, in this carbon range, austenite is stable. Yeah. Now, if you show the middle left of the diagram, how ferrite and cementite, if you look down, you can see how ferrite and cementite are both stable at lower temperatures across quite a wide range of carbon contents. Yeah, here. So across this whole region here, ferrite and cementite are stable. Here, ferrite and austenite are stable. So if you had a certain carbon content, say 1 weight percent, you had it at 1600 degrees and you cooled it, you could predict the change in microstructure as you cool. It's a little bit more complicated, and we'll talk about eutectics and things like that later on. But for now, we'll just show what phase diagrams can do. You've got dotted lines there. They denote phase boundaries for iron graphite, but I won't overwhelm you with that just yet. Don't worry about them. We'll leave that for another day. Because that's it for lecture 1. We've covered quite a fair amount of the fundamentals, so don't panic if you feel a little bemused. I strongly suggest you go over what we've covered today again as soon as possible, and you'll soon find it. Pardon the pun. It's cemented in your mind. I'm sorry, cemented in your mind for the next lecture. But until then, look after yourselves, and I'll see you for lecture 2 soon.